Have you ever gazed up at the endless blue, watching a colossal metal bird effortlessly carve a path across the sky, and wondered, how on earth does that thing stay up there? From the sleek, modern jets whisking us coast to coast over the sprawling landscapes of America, to the nimble propellers that first took flight on the sands of Kitty Hawk, North Carolina, the mystery of flight often feels like pure magic. But it's not magic at all. It's a magnificent ballet of science, engineering, and some fundamental principles of physics. Let's unravel this complex concept, turning a marvel of modern engineering into something wonderfully understandable. At its core, airplane flight is about four primary forces constantly battling and balancing each other: lift, gravity, thrust, and drag. Think of them as the invisible hands pushing and pulling on the aircraft at all times. First, there's gravity, the force we're all intimately familiar with. It's Earth's constant tug, relentlessly pulling everything downwards, including our airplane. To fly, a plane needs to generate an opposing force that's stronger than gravity. That force is lift. Lift is what pushes the plane upwards, defying gravity. Then we have thrust. This is the forward-moving force that propels the aircraft through the air. Without thrust, a plane would simply be a very heavy glider. Thrust is typically generated by powerful engines, either jet engines or propellers, pushing air backward to propel the plane forward. Finally, there's drag. This is the resistance the air puts up against the plane's forward motion. It's like an invisible hand trying to slow the aircraft down. Engineers design planes with incredibly smooth, aerodynamic shapes to minimize drag, allowing the plane to move through the air more efficiently. Now, let's dive into the most fascinating of these forces: lift. How exactly does an airplane generate enough lift to overcome gravity, especially when it weighs hundreds of thousands of pounds? The secret lies in the shape of its wings, or what engineers call an airfoil. If you look closely at an airplane wing, you'll notice it's not flat. It's curved on top and flatter on the bottom. This specific shape is critical. As the plane moves forward, powered by thrust, air rushes over and under the wings. Because of the wing's curved upper surface, the air traveling over the top has a longer distance to cover than the air traveling underneath. To meet up with the air from below at the trailing edge of the wing, the air on top has to speed up. This is where Bernoulli's principle comes into play. It states that as the speed of a fluid, in this case, air, increases, its pressure decreases. So, the faster moving air over the top of the wing creates an area of lower pressure. Meanwhile, the slower moving air underneath the flatter bottom of the wing creates an area of higher pressure. This difference in pressure, higher pressure below, lower pressure above, literally pushes and pulls the wing upwards, creating lift. It's like a giant invisible hand lifting the plane into the sky. But Bernoulli's principle isn't the whole story. Newton's third law of motion also plays a crucial role. For every action, there is an equal and opposite reaction. The wing isn't just sitting there. It's angled slightly upwards relative to the oncoming air, a concept known as the angle of attack. As the wing slices through the air, it actually pushes a massive amount of air downwards. And in reaction to the wing pushing air down, the air pushes the wing up. Think of sticking your hand out of a car window and tilting it slightly. The air pushes your hand up. An airplane wing does this on a much grander, more sophisticated scale. So, lift is a combination of these two powerful principles working together. The pressure differential created by the airfoil shape, and the downward deflection of air by the wing's angle of attack. With lift explained, let's revisit thrust. Jet engines, common on airliners you see flying over cities like New York or Los Angeles, work by sucking in huge amounts of air, compressing it, mixing it with fuel and igniting it. This creates a powerful blast of hot, high-velocity exhaust gases that shoot out the back of the engine. This action propels the plane forward, providing the thrust needed to overcome drag and generate sufficient airspeed for lift. Propeller planes work similarly but use spinning blades to screw their way through the air, pushing air backward to move the plane forward. Once a plane is airborne, pilots don't just point it and hope for the best. They have incredible control over all these forces. Small movable surfaces on the wings and tail allow them to manipulate lift, drag, and even the direction of thrust. Ailerons on the wings control the plane's roll, making it bank left or right. Elevators on the horizontal tailplane control the pitch, moving the nose up or down to climb or descend. The rudder on the vertical tail fin controls the yaw, moving the nose left or right. Flaps on the trailing edge of the wings extend during takeoff and landing, increasing both lift and drag to allow the plane to fly slower without stalling, and to slow down for landing. So, when an aircraft like a Boeing 787 Dreamliner accelerates down the runway at Dulles International, its engines are generating immense thrust, overcoming drag. As speed increases, the wings begin to generate more and more lift. When lift finally exceeds gravity, the aircraft lifts off the ground, ascending gracefully into the sky. In cruising flight, high above the clouds, perhaps over the vast prairies of Kansas, the pilot balances these four forces so that lift equals gravity and thrust equals drag, allowing for stable, efficient flight. For landing, the pilot reduces thrust, extends flaps and landing gear to increase drag and reduce lift, allowing the plane to slow down and descend safely to the runway. From the pioneering spirits of the Wright brothers who first dared to dream of flight, to the intricate design and sophisticated control systems of today's commercial airliners, the ability of an airplane to fly is a testament to human ingenuity and a deep understanding of the natural world. It's not magic, it's the beautiful, intricate dance of physics. Next time you hear the roar of a jet engine or see a plane soaring effortlessly overhead, take a moment. Appreciate the marvel of engineering, the invisible forces at play, and the incredible science that makes even the most massive of machines defy gravity and soar across continents, connecting us all under the same vast, blue sky. It's a truly breathtaking feat.